You think you understand gravity? Step on a scale. See the number. That's your weight. Earth pulling you down. Simple, right? Except you're fundamentally wrong about what's actually happening. Not a little bit wrong. Not missing some details wrong. Fundamentally, completely wrong about what gravity even is. Here's what's strange. This mysterious pull everyone talks about? You've never felt it. Not once in your entire life. Think about that. You say you feel gravity right now, but what you actually feel is the floor pressing against your feet, pushing up. Always pushing up, never pulling down. So where's this pull? What's doing the pulling? And here's the thing that should break your brain. Gravity isn't a force at all. And when you finally see what gravity really is, when you really see it, the whole universe starts to look different. Let me show you. Stand up right now. Feel your weight. What are you feeling? You say gravity, Earth pulling you down. That's what everyone says. But think about the actual sensation. Really think about it. The floor pressing against your feet, pushing up. Your chair pressing against you, pushing up. That's what you feel. This mysterious pull everyone talks about? You never feel it. Not once. You only feel the push. Always pushing up, never pulling down. So where's this pull? What's doing the pulling? And here's something stranger. The moon is falling toward Earth right now. Has been falling for billions of years. About 4.5 billion years, actually. But it never gets closer. Just circles. Always falling, never landing. What kind of pull works like that? A pull that pulls forever, but never pulls anything in. And according to Newton, that pull happens instantly. Move Earth, and the moon feels it immediately. Across 240,000 miles of vacuum. That's about 384,000 kilometers. Instantly. How? What carries the message? What's the mechanism? Newton himself couldn't explain it. He called it action at a distance, and admitted he didn't understand how it worked. The mathematics was beautiful. The predictions were perfect. So people stopped asking uncomfortable questions. They shouldn't have stopped. Because when you finally understand what's really happening, everything changes. The floor isn't resisting gravity. You aren't being pulled anywhere. Something far stranger is going on. Go back several centuries. Nobody understood how planets moved. Copernicus said they orbit the sun. Fine. But how? What paths do they follow? Why those paths and not others? Tycho Brahe built an observatory, and he spent decades recording planetary positions, night after night, year after year, measuring angles with brass instruments to fractions of a degree. Why such precision? Because you can't understand nature by guessing. You have to look. Measure carefully. Write down exactly what you see. That's where real science begins. His data reached Johannes Kepler. Kepler wanted to find the shape of planetary orbits. He tried circles. The predictions were close, but Mars was off by 8 arc minutes. That's 8/60 of a degree. Tiny. Most people would shrug that off as measurement error. But Kepler knew Tycho's precision. That man didn't make 8 arc-minute errors. His instruments were too good. His measurements too careful. So Kepler threw out his theory and started over. After years of work, he found it. Ellipses. Planets move in ellipses with the sun at one focus. Perfect match to the data. Beautiful. But it raised a bigger question. Why ellipses? What makes planets follow that shape? Meanwhile, Galileo was doing simple experiments, rolling balls down ramps. Sounds trivial, but watch what happens. Roll a ball down an incline. It speeds up. Let it roll onto a flat surface. It keeps going. Doesn't stop immediately. Now imagine you could eliminate all friction. What would happen? The ball would roll forever. Same speed, same direction. Forever. This bothered people. Surely motion requires a continuous push. Surely things naturally come to rest. No, that's backwards. Motion is natural. An object moving in a straight line doesn't need explanation. That's the default state. What needs explanation is change. Slowing down? That's friction. Speeding up? That's a push. Changing direction? That's a sideways force. This is inertia, the first law of motion, and it creates a puzzle. Planets should move in straight lines, that's their natural state. But they don't. They curve. Their paths bend continuously toward the sun. Something must be deflecting them every instant. What? Adam Newton saw it clearly. Planets want to go straight. That's inertia. That's their natural state. But they don't go straight. They curve. Their paths bend continuously toward the sun. Something must be changing their motion constantly. Every instant, every second. Newton called it gravity, universal attraction between any two masses. And he figured out the rule. The force depends on two things, mass and distance. More mass, stronger force. The sun pulls harder than a pebble. Greater distance, weaker force. But not just proportionally weaker. Gravity drops with the square of distance. Double the distance, force becomes 4 times weaker. Not 2 times, 4 times. Triple the distance, 9 times weaker. With this one principle, everything fell into place. Why ellipses? Because planets are falling toward the sun, while simultaneously moving sideways. The combination creates elliptical paths. Kepler's laws? They emerge naturally from Newton's force law combined with inertia. Why does the moon orbit Earth? Same principle. It's falling toward Earth, but moving sideways fast enough to keep missing. It falls around Earth instead of into it. Why does an apple fall? Earth attracts it. Same force, same law, just different scale. Newton did a beautiful calculation. He figured out how much the moon falls every second, how much its path deviates from a straight line. Then he calculated how much objects fall on Earth's surface. The numbers matched perfectly. When accounting for distance, revolutionary. The force pulling an apple is the same force holding the moon in orbit. Heaven and earth, same physics. With Newton's law, everything made sense. Ocean tides, the moon pulls on Earth's water. Earth's equatorial bulge, it spins, so stuff at the equator wants to fly outward. Gravity pulls it in. Balance creates the bulge. Comets? They follow elliptical orbits just like planets, returning on predictable schedules. Strange observations found explanations. Jupiter's moons sometimes appeared early, sometimes late. Turned out, light takes time to travel. When Earth is farther from Jupiter, light takes longer to reach us. This led to measuring light speed for the first time. Planets wobble slightly because they pull on each other, not just on the sun. From the wobbles in Uranus's orbit, astronomers predicted a new planet. Neptune, and found it exactly where predicted. For 2 centuries, Newton's law of gravity stood as one of the greatest achievements in science. It explained everything anyone could measure. But there was one detail nobody could explain. Drop a hammer and a feather in a vacuum. They hit the ground at the same time, exactly together. The hammer has more mass, so according to Newton, gravity pulls it harder, much harder. But the hammer also has more inertia. It resists acceleration more, much more. These 2 effects cancel, not approximately, perfectly. Every object falls at the same rate, regardless of mass. Why? Newton's theory requires 2 different properties of mass. Gravitational mass. This determines how strongly objects attract each other, how much gravity pulls on something. Inertial mass. This determines how hard it is to accelerate something, how much it resists being pushed. These are different concepts, different properties. One is about attraction. The other is about resistance to motion. And yet, they're always perfectly proportional. For every substance ever tested, gold, iron, wood, water, anything, to incredible precision, parts per trillion. But why? Why should the attracting property of mass and the resisting acceleration property be perfectly equal? Newton had no answer, just the remarkable coincidence that made the mathematics work beautifully. Or was it a coincidence? Einstein asked a different question. What if it's not a coincidence? What if that perfect equality is telling us something fundamental about what gravity really is? Newton asked, how does gravity pull across empty space? For 200 years, physicists tried to answer that question. Einstein did something different. He didn't answer Newton's question. He rejected it entirely. What if there is no pull? What if objects aren't being pulled at all? What if they're just moving naturally? Here's a thought experiment. You're in a closed room with no windows. You feel your normal weight pressing you to the floor. Are you on Earth? Or are you in a rocket in deep space, accelerating upward at 9.8 meters per second squared? That's about 32 feet per second squared. Can you tell the difference? Drop something. It falls to the floor. In both cases. Throw a ball horizontally. Curved path. In both cases. Stand on a scale. Same reading. In both cases. There is no experiment that can distinguish them. Think about that. You're a scientist in this room. You have every instrument ever invented. And you cannot determine whether you're sitting still in a gravitational field or accelerating through empty space. This is the equivalence principle. If you truly cannot tell gravity from acceleration, maybe they're the same thing. Maybe what we call sitting still in a gravitational field is actually a form of acceleration. Here's Einstein's revolution. Objects in free fall have no force acting on them. The falling apple, the orbiting moon, astronauts floating in space capsules, satellites circling Earth. None of them experience any force. Meta pause, sex 1.0. They're moving naturally, following their natural paths. No forces, no pulls, nothing acting on them. But wait, the apple is clearly falling, accelerating toward Earth. Yes, but what if the apple isn't accelerating at all? What if it's following the straightest possible path, and it's space itself that's curved? This is Einstein's profound insight. Gravity is not a force between objects. Gravity is the curvature of space and time. Massive objects don't pull on other objects. They warp the space around them. They bend it, curve it, distort the geometry. The apple isn't being pulled to the ground. It's following the straightest possible path through curved spacetime. But spacetime near Earth is curved, so straight points toward Earth's center. The ground pushes you upward, preventing you from following that natural path. That's what you feel as weight. Not gravity pulling down, the ground pushing up, deflecting you from your natural trajectory through curved spacetime. Einstein made a concrete prediction. If gravity is really curved spacetime, then light should be affected too. Light has no mass. In Newton's theory, gravity shouldn't affect light at all. But if gravity is curvature of space itself, then light following the straightest path through curved space should bend. During a solar eclipse in 1919, astronomers measured the positions of stars near the sun's edge. The stars appeared displaced from their true positions. The starlight had bent, passing near the sun, curving around the warped spacetime, exactly as Einstein predicted. This was direct evidence. Space itself curves in the presence of mass. Now here's something that confuses everyone. Astronauts in orbit look weightless, floating around. Zero gravity up there, right? Wrong. The gravitational field at satellite altitude, a couple hundred miles up, is about 90% as strong as here on Earth's surface. So why do astronauts float? Because they're falling. The capsule is falling. Everything inside is falling toward Earth constantly. But they're also moving sideways, very fast, about 17,000 miles per hour. That's roughly 27,000 kilometers per hour. As they fall, Earth's curved surface falls away beneath them. They keep missing. They fall around Earth instead of into it. Everything falls together at exactly the same rate. So there's no sensation of falling, no weight, no sense of up or down. It feels exactly like floating in empty space, far from any mass. This is equivalence in action. Free fall in a gravitational field feels identical to floating freely in empty space, because they are the same thing. In free fall, no force acts on you. You're following the natural geometry of curved spacetime. Remember that scene in Interstellar? The astronauts land on a planet near a black hole. They spend a few hours there. When they return, decades have passed for everyone else. That's not Hollywood magic. That's curved spacetime. Gravity doesn't just bend space, it bends time. Clocks near massive objects run slower. Metapause, sex, 1.0. And this isn't just theory. GPS satellites have to correct for this. The clocks up there run slightly faster than clocks on Earth, because they're farther from Earth's mass, in weaker curved spacetime. If we ignored Einstein, your GPS would be off by kilometers within a day. Every time you use Google Maps, you're relying on Einstein being right about gravity. Think of an ant walking on a curved surface. The ant thinks it's walking a straight line. But from outside, we see it's following a curve. The ant can't perceive the curvature. It just goes straight ahead. That's what's happening with everything near Earth. Except it's not just space that's curved. It's space and time together. Space-time. And here's something beautiful. Why is Earth round in the first place? Because of gravity. But not in the way you think. It's not that some force is pulling everything toward the center, molding Earth into a sphere. It's that space-time around Earth's mass is curved equally in all directions. Every piece of rock, every drop of water, is trying to follow the straightest path through that curved geometry. And when everything follows those curves from all directions equally, you get a sphere. The only shape where every point on the surface is the same distance from the center. Earth is round because that's what happens when matter follows curved spacetime. The shape emerges naturally from the geometry. You're standing right now. You feel weight. In Newton's picture, gravity pulls you down, and the floor pushes you up. Two forces. Balanced. In Einstein's picture, only one force acts on you, the floor pushing up. But if there's only one force, you should be accelerating. And you are. You're accelerating upward, constantly. Think about that. Right now, sitting still, you're accelerating upward at 9.8 meters per second squared. That's about 32 feet per second squared. The natural path through spacetime points toward Earth's center. That's the freefall trajectory. That's where spacetime says you should go. But the floor is in your way. It pushes you upward, deflecting you from that natural path. You're like someone standing in an accelerating rocket. The floor pushes. You feel weight. Not from any downward pulling force, from being accelerated away from your natural path. Now think about the apple hanging in a tree. It's also being pushed upward by the branch. When the branch breaks, what happens? The pushing stops. The apple is suddenly free to follow its natural path through curved spacetime. It falls. But here's the mind-bending part. The apple isn't accelerating. The apple is finally free to move naturally. You, standing on the ground, are being constantly accelerated upward by the floor pressing against your feet. Falling is the natural state. Standing still requires a force. That's Einstein's revolution. Now, here's a thought experiment that should change everything. Imagine gravity disappeared for 1 second. You wouldn't float gently upward. That's the wrong picture. The floor would stop pushing. You'd finally be free to follow your natural path. But so would everything else. The atmosphere would expand into space, nothing holding it to Earth. The oceans would drift away, water following its natural path. The Earth itself would stop being round. Without curved space-time holding it together, matter would have no reason to form a sphere. The planet would begin to disintegrate. Every rock, every drop of water, every molecule following its own straight path through now flat space-time. That's how fundamental gravity is. Not a force pulling things together, the very geometry that gives the universe its shape. Without curved space-time, there would be no planets, no stars, no galaxies, no structure at all. Just particles drifting through empty, flat space. Forever. A star is essentially a massive ball of gas. Its mass creates a deep well in space-time. The natural paths in that curved space point inward. So what prevents the star from collapsing? Pressure. Nuclear reactions in the core pushing outward. Fusion releasing enormous energy. Balance. For billions of years, this balance holds. The Sun has been doing this for about 4.6 billion years. But eventually, the nuclear fuel runs out. The pressure drops. Balance breaks. The star collapses. If the star is massive enough, the collapse continues until matter is compressed to incredible density. Atomic nuclei merge. Electrons are crushed into protons. What emerges is a neutron star. Nuclear matter, compressed to the size of a city. A teaspoon of this stuff would weigh about 1 billion tons. That's roughly 900 million metric tons. But for even more massive stars, not even neutron pressure can stop the collapse. Spacetime curves so sharply that all possible paths lead inward. Even light, following the straightest possible path through this geometry, spirals inward and never comes out. This is a black hole. We can't see black holes directly, but we see their effects. Matter falling toward a black hole speeds up, heats up, radiates enormous energy before disappearing. All from one idea. Mass curves spacetime. Objects follow the curves. From this one principle, everything follows. Planetary orbits, tides, the precession of Mercury's perihelion. A tiny effect Newton's theory couldn't explain, but Einstein's predicts perfectly. Gravitational lensing, light bending around galaxies, black holes. Gravitational waves rippling through space when massive objects collide. The same principle explaining how the moon orbits also explains the largest structures we observe. Galaxies, clusters of galaxies, the cosmic web stretching across billions of light years. Universal, elegant. The pattern in the small piece reveals the design of the whole fabric. So what is gravity? Not a force, not a pull, not something reaching across space to grab you. Gravity is the shape of spacetime itself. Mass curves the geometry of space and time. Objects follow the straightest paths through that curved geometry. That's it. That's the whole story. The apple isn't pulled to the ground. It's following its natural path through curved spacetime. The moon isn't being held in orbit. It's falling freely, forever, through the curved geometry around Earth. You, standing here right now, you're not being pulled down by any force. You're being pushed up, by the floor. Constantly accelerated away from your natural path through spacetime. That's the paradigm flip. Falling is natural. Standing still requires a force. Newton gave us a beautiful formula. It works for almost everything. But Einstein revealed what gravity actually is. Not a mysterious force acting at a distance. The very geometry of the universe. And now you know. Not just the formula, not just the predictions. The truth about what's actually happening every time something falls. If this changed how you see the universe, even a little bit, drop a comment below. Tell me what clicked for you. Subscribe if you want more physics explained the way Feynman would have explained it. No memorization, just understanding. And I'll see you in the next one.